So the whole point of yesterday's lesson was to learn how to complete the square. And why did we want to know how to complete the square? Because it allowed us to take a equation in the standard form equation, y is equal to ax squared plus bx plus c, and it allowed us to convert that into the vertex form. Why would we ever want the vertex form in the first place? Because when we have a vertex, that means we know the maximum or minimum of our parabola or of the equation. So if we can take that knowledge, that means that we can find the maximum or minimum of whatever problem we're dealing with at that point. So that's what today's lesson is all about, the maximum and minimum applications. So we're going to take the knowledge that we learned yesterday of completing the square, and we're going to apply it to a number of different types of problems today as well as during the next lesson. So there are many real-world applications involving optimization of quadratic relations. Of course there are. Common types of word problems that we're going to see, at least today, are going to be formula problems and revenue problems. So formula problems, just regular old problems that we're going to make calculations for, and revenue problems are where we're talking about money, maximizing profits or minimizing losses. Okay? So in order to find the maximum or the minimum of, where'd my pen go here? There we go. In order to find the maximum or minimum value, what we're going to do is we're going to create a quadratic relation, and we're going to use all the information provided in the problem. That's going to help us create that relation. Hopefully, it won't be too much effort. Sometimes they'll even give us the actual relation in the problem themselves, but other times we may have to create it from scratch. We have to make sure that we understand what our unknowns are, so we have to make sure to use let statements in order to introduce any variables. Then we're going to write our relation in vertex form. Usually this is going to require us to do completing the square. And if you forget how to do that, go back to yesterday's lesson and refresh your mind. Okay? All right. So the maximum minimum value is always going to be the y value of the vertex. It's always the y value of the vertex. Now, this is going to be helpful because it's going to allow us to actually determine the solution to whatever problem is we're trying to work with. Now, the a value, remember what the a represents. The a represents two things. It represents reflection in the x-axis as well as stretches or compressions. What we're talking about, or what we care about right now, is whether it's reflected or not. So remember, if the a value is positive, that means that the curve opens up, so we have a minimum value. So that means the curve looks something like this. So we have a minimum value. However, if the a value is negative, that means the value is going to be a maximum. Maximum means largest. So that means the curve is something more like this. And we get the maximum value therein. Okay. And of course, as we're always going to do, because they're always word problems, we always need to have some form of concluding or therefore statement to finish it off. So we need some form of concluding or therefore statement. Oops. I will get better at writing with this tablet at some point, hopefully. Anyways, so let's get to our first problem. So the path of a ball being kicked is modeled by the relation h is equal to negative 5t squared plus 10t plus 60, where t is the time in seconds and h is the height of the ball in centimeters. So we were given quite a bit of information there. First of all, we were given the unit, so we know what we're dealing with here, although that unit does seem a little awkward considering we're talking about kicking a ball. But we didn't make the problem. It is what it is. We were also given what the variables are. T is time and h is the height. Okay? So h, if we're thinking about a graph, basically what they're saying here, t is the x-axis and h is the y-axis. Okay. Now, our job is to find the maximum height of the ball, or maximum height the ball reaches. So that ball is going to fly through the air, and it's going to hit some kind of maximum. How do I know for sure it's going to be a maximum? Because the a value in front of the t squared is a negative value. So it's definitely going to be a maximum. So in order to do this, we are going to have to complete the square for this quadratic relation. We need to put it into vertex form so we can actually do something useful with it. So let's start the process. We're starting over here with h is equal to negative 5t squared. So let's write that out. H is equal to negative 5t squared plus 10t plus 60. Now, if you remember how to do this, our first step is we want to factor out the entire a term from the first two terms of our quadratic relation. So we're going to factor out negative 5. That means the negative 5t squared just becomes t squared. And the 10t becomes negative 2t. Remember, we're dividing out a negative 5. And then we leave the plus 60 alone. Now, what's the next step? The next step is we look at the second term. We leave the negative 5 alone here. We look at the second term. Leave all this. The second term is a negative 2. So what we're going to do is we're going to take that term, we're going to divide it by 2. And then we're going to square it. So negative 2 divided by 2 is negative 1. Negative 1 squared is just 1. So now what we're going to do is we're going to add and subtract. I suppose I should make sure that my t's actually look like t's. Let me erase that. Don't want them getting confused with my plus signs here. So we have negative 2t. I think I deleted my 2 here. Negative 2t plus t. No, should be plus 1. Plus 1 and minus 1. Come on, computer. Can't be lagging already. So we're going to add and subtract that 1. And then what we have to do is we have to take the negative 1 outside the brackets. But in order to do that, we have to multiply it by the a term. So let's fix this. Anybody else see what just happened there? Okay. Negative 2t. Oh, it killed one of my brackets there. And now we're going to add 1 and we're going to subtract 1. And then the plus 60 is still on the outside. Now we want to bring this negative 1 outside. So in order to do that, we have to multiply it by the a term. Otherwise, the math breaks. So inside we have negative 5 still, t squared minus 2t plus 1. That's the end of our bracket there. And then on the outside we have plus 60. Now it's minus 1 times minus 5, so that'd be plus 5. So what do we end up with here? So we have h is equal to the negative 5 gets left alone. And now we have a perfect square trinomial inside. So we take the square root of the first term. We take the sine of the second term. And then we take the square root of the third term, which is just 1. And that whole thing becomes squared. And then on the outside we have our plus 65. So from this, we can see that our vertex is hk. H is a 1. And k is a 65. What does that tell us? It tells us, remember, our maximum is the y value. Our maximum is the y value of our vertex. So therefore, the maximum height of the ball is 65 centimeters. That seems pretty ridiculous, but whatever. It's not our game. So that's everything we needed for the first part of the question. Our first job in all these questions is basically to use the completing the square strategy to put it in vertex form, because that's going to tell us our maximum or minimum. Okay. How long does it take the ball to reach the maximum height? Basically what it's asking us right now is, what is t when we're at the maximum? So what is t? What is t at the maximum? Well, that's the other part of the vertex. So we don't even have to do any calculations here. We simply need to look at the vertex, and we can see that it takes 1 second. All right? So that's our question. So our answer is, it takes 1 second, which makes more sense for the 65 centimeters now. It takes 1 second to reach the maximum height. Even that actually is kind of silly. Should have got there a lot faster to reach 65 centimeters. All right. At what time? So now we're looking for a t. So what is t? So at what time is the ball 20 centimeters high? So what is t when h is equal to 20? So whenever you see a question like this, it's just a matter of substitution. We're going to substitute that into our relation to solve for t. So where's our relation? Our relation is way up here, so we could use the original relation. We could also technically use the vertex form relation as well. It doesn't really make a difference because you should still end up with the exact same value. For this situation, I guess I'll substitute it into the vertex form version. Again, it doesn't really make too much of a difference. You should end up with the exact same number. Just maybe look at the equation and see which one is more complicated to work with. So here's our equation. H is equal to -5. And now I have t, which is what I'm trying to solve for, minus 1 squared plus 65. Now let's substitute our h is equal to 20 in there. So we get our 20 in here equals -5 t minus 1 squared plus 65. Now we need to bring that 65 over to the other side. Remember, whenever you're trying to isolate for a variable in an equation, you're basically following BEDMAS backwards. So I want to do additions and subtractions first, then I'll handle my divisions and multiplications, then I'll do my exponents, and then I'll do my brackets. Okay, so I'm going to start with my additions and additions and subtractions first. So I'm adding this 65. So I need to do the opposite operation to both sides. So that means 20 minus 65 is -45 equals -5 t minus 1 squared. And the 65 cancels out. Now I got to go divisions and multiplications. I only have one, just this -5. So it's being multiplied, -5 times t minus 1 squared. So that means I have to divide both sides by -5. So -45 divided by -5 is just 9. Equals t minus 1 squared. Now I got to go to exponents. I do have an exponent. I have a square. So in order to get rid of the square, that means I need to take the square root of both sides. The square root of 9 is just 3. Equals t minus 1. And then finally, that means t is equal to, I got to bring that minus 1 over to the other side. 3 plus 1, t is equal to 4. And there we go. So I should probably back that up a little bit because, yeah, we got to think of something here. I don't want to steer people wrong here because we do run into some sticky situations. So let's back this up just a little bit. That's not a wrong answer. We just have to add more to it. Okay? So we have to remember when we take the square root of both sides, what we're actually getting is plus or minus. Let me write this out in more steps actually because I don't want anybody to get confused what's actually happening here. I don't know why it doesn't want to let me erase that, but whatever. Okay, so let's put our bracket in there, and let's bring this back over to the other side here. So I'll rewrite this. So this is 9 equals t minus 1 all squared. Now I need to get rid of that square, so that means I need to take the square root of both sides. So that means it's the square root of 9, but it's plus or minus the square root, because plus 3 squared is 9, minus 3 squared is also 9. So it actually is both options. So we have to handle both situations, and that's going to be equal to t minus 1. So this is going to be plus or minus 3 is equal to t minus 1. So if it's positive, in one situation, if it's positive, then that's going to be 3 equals t minus 1, or t, oh my goodness, what is going on here? T is simply equal to 4, which is what we had before. This is getting too cluttered. I don't like that at all. There we go. All right, so we had 3 over here. So we're bringing that minus 1 to the other side. So we end up with 4 equals t, or t equals 4, same thing. And that's a perfectly reasonable solution. However, that's when we added the 3. What if when we subtracted the 3? In this situation, we end up with -3 equals t minus 1. -3 plus 1, that's -2 equals t. Now think logically for a second. We're talking about time. How can time be negative? So in that situation, what that means is that we're going to reject this answer. Okay? Because in this context, time cannot be negative. Reject. Time cannot be negative. Now this is important because we're going to come across this same situation in a lot of our problems. Where we're going to end up with two possibilities. One of them is almost always going to get rejected. So we have to think about this. So I'm going to write a therefore statement, which is going to include this rejection. So since time cannot be negative in this scenario. Sometimes it can be in some other scenarios. So since time cannot be negative in this scenario, that means t is equal to -2 is impossible. Therefore, the ball is at a height of 20 centimeters after 4 seconds, or at 4 seconds. The ball is at a height of 20 centimeters at 4 seconds. There we go. So a lot of our problems are going to take the same process. All right. Almost always our first step is going to be use completing the square to put it into vertex form, unless we already have vertex form. Once we have vertex form, that'll tell us our maximum or minimum, depending on what the problem is looking for. Once we have that, we can then find the solution to a whole bunch of other problems. It depends on what the question is actually asking. But that is really the key. Get it into vertex form to figure out your max and min. So let's go on and let's try another question. We'll start here. All right. So on a forward somersault dive, the diver's height, that kind of just jumped right into the question, didn't even tell us we're talking about a diver, but whatever. On a forward somersault dive, the diver's height, h in meters, above the water is given approximately by h is equal to -5 t squared plus 10t plus 3. This is actually very similar to our last equation if you look at it. The only difference is the amount of the c term. In that case, it's plus 60. Here, it's plus 3. T is our time in seconds after he leaves the board. All right. Find the diver's maximum height above the water. As usual, our first step is going to be the same. Use completing the square to put it into vertex form. So we have h is equal to -5 t squared plus 10t plus 3. And we got to factor out the entire a term. That's a terrible 3. There we go. We're going to factor out the entire h term, or a term, I apologize, -5. That means this becomes t squared, and this becomes -2t. And we still have our plus 3 on the outside. Now, remember what we have to do. Next step is rewrite all of this stuff, -5 t squared minus 2t. And now we got to take half of the second term and then square it. So 2 divided by 2 is 1, squared is +1 and -1. And then we have plus 3 on the outside. We want to bring the -1 outside, so we have to multiply it by a to do that. So it's going to be -1 times -5, which is just going to be 5. So now we're sitting here with h is equal to -5 t minus 2t plus 1. And on the outside, we have plus 3 and then plus 5. And we're going to finish this off with h is equal to -5 times our perfect square trinomial. Oops, this should be t squared. T minus 1 squared plus 8 on the outside. So that means we have a vertex of 1, 8. So what that tells us? It tells us that our max is always the y term. So therefore, the maximum height of the diver is 8 meters. That's pretty high. All right. How long does it take the diver to reach the maximum height? Again, this is saying when we're at the maximum height, what is the time? Well, remember, the time is the other value here. This is the x component of our vertex. So we just have to look at the vertex and see this. Oh, it took 1 second. So we don't have to do any calculations or anything like that. We just have to look at it and observe in this situation. Sometimes there'll be calculations, but not in this case. So It takes 1 second for the diver to reach maximum height. Alrighty. How high is the board above the water? What is this actually asking us? It's asking us for the initial height. What does initial mean? Initial means start. So it's asking us for the starting height. So if h is the value we're looking for, what is h? Then that means we need to know t. When t is equal to what? Well, this is a starting height. What is the value of time when we're first starting the problem? Well, he hasn't dove yet. What does that mean? That means no time has passed. So we're asking, what is h when t is equal to 0? All right? Whenever you're asked for the initial height or something like that along those lines, you're almost always going to be talking about when t is equal to 0. Can there be exceptions to this rule? Sure, I guess. It depends on the problem. Somebody might come up with some creative problem about negative time and stuff, but most of the time we're going to talk about when t is equal to 0 when we're talking about initial values. So how high is it above the water? So that means we just need to substitute, okay? We're going to substitute 0 into our equation. Now, we can substitute it into either equation. It will work just fine. Now, last time I substituted it into vertex form, if you recall that. So in this time, I'm going to substitute it into the original relation, just so you can see that we can do both. All right? So that means we have h. We're trying to find h. And we're saying, where is it? Equals -5 t squared. What is t? T is 0 squared plus 10 times 0, which is t, plus 3. Well, 0 times anything is 0. Plus 10 times 0 is still 0, so we're at 0 plus 3. So that means our answer is just h is equal to 3. So therefore, the initial height of the board or the initial height of the diver, oh no, it is asking for the board. So the initial height of the board is 3 meters. Wow, that's a pretty good jump. He went from 3 meters to 8 meters. That's a vertical jump of 5 meters. That's impressive. All right. So that's pretty awesome. That gave us information about where it started. We can actually even think about drawing it. This question doesn't ask us to draw in any way, shape, or form, but that doesn't mean we can't. We know that it gets up to a maximum of 8, and it starts at 3, and it's going to go through the air, hit that peak, and then come down and hit the water at some point. And we know a whole bunch of information. We know that this is at 1 second. And so our vertex is 1,8. We can draw this diver's entire path pretty much. How long will it take the diver to enter the water? So you can look at this in two ways. The first way is to just understand symmetry. You know that it is a symmetrical curve. So at 1 second it hits 8, and that's great. And ideally, it's going to hit it pretty similar on the other side, but it's not going to be perfect because remember, the diver is starting at a height of 3 meters. For this to be perfectly symmetrical, that would mean that we'd be leaving from the x-axis, but we're not. We're actually leaving a little bit higher up. So we can't just use symmetry and say, oh, it's going to be 2 meters, because it's not. Or 2 seconds. It's not going to be 2 seconds. So now we have to go in and we got to do math. What are we actually trying to calculate? How long? So we're looking for time. So what is t? When? Our only other variable is h. So how long will it take for the diver to enter the water? What is h when the diver enters the water? How high is the diver when they enter the water? They're at a height of 0. They're in the water. So that means, what is t when h is equal to 0? That's what we're trying to solve. So we're going to substitute h is equal to 0 back into our relation. And we're at the same situation again. So we could put it into either equation, okay? Or we could, I guess we could choose, but we're going to put it into our vertex form equation this time. So let's do this. So we have 0 is equal to negative 5 times t minus 1 squared plus 3. That's our equation. So now we need to solve for our value of t. So we're going to bring the negative 3 to the, or we're going to bring the positive 3 over to the other side. So that means we have negative 3 over here. I'm just going to scroll down a little bit so we have a little bit of screen real estate. So we have negative 3 equals negative 5 times t minus 1 squared. And now we got to get rid of this negative 5. So we got to divide both sides by negative 5. So that means we're at 3 over 5 equals t minus 1 squared. Uh-oh. Okay. That doesn't mean we're done. We got to get rid of the square. That means that we need to take the square root of both sides. Remember, when we do this, we got to look at the fact that we are going to get both the positive and negative version of this. So we have the positive and negative version of 3 over 5 is equal to t minus 1. So that means that t is equal to positive or negative, the square root of 3 over 5. Now that minus 1 is going to go over to the other side, so it's going to be plus 1. So we have to look at both options here. What are our options? Well, one option is we're adding and one option is we're subtracting. So let's say that we're adding. So that means we have the square root of 3 over 5. So this is where you're just going to pump it into your calculator at this point, okay? Is it 3 over 5 or is it... did I make a mistake somewhere? I did. Oh, I did. Something... Where did I make that mistake? Yes. It should be an 8. That should be an 8. Silly me. Give me 1 second to think about this. Yeah. Oh no, so this math is still right down here, but this should have been 8 because we substituted into the original equation. So that's no problem. But down here, this should be an 8 over here. Okay? Because we're using our vertex form equation. Here I use the original equation, which has a plus 3 in there, and that makes perfect sense. But down here, I use the vertex form. This 3 should actually be an 8. So let's fix our math. Hopefully you guys caught that while we started this, but I don't know if you did. I'm going to fix it over here too, ideally. And we're going to try and fix it over here. I love that it's taken away everything that I don't want it to take away. There we go. Let's see if we can clean this up. So this should be an 8, which means it becomes a negative 8 over here, which means this becomes 8 over 5. Okay. And then on the opposite side over here, we have plus or minus the square root of 8 over 5. And here we have plus or minus the square root of 8 over 5. And that should be an equal sign there. Okay, we got it all fixed. So that means, I apologize for that. We have, over here, we're going to have the positive of 8 over 5 plus 1. And down here, we're going to have the negative square root of 8 over 5 plus 1. That is a negative there. Now, you're going to end up with some approximate numbers here because these are not a nice perfect number by any means. So the first number we're going to get for the positive one is going to be a 2.3. And the bottom number is going to be negative 0.3. Whoa. We did it again. We ended up with a negative time. So we are going to reject this because we can't. It doesn't make any sense in the context of this problem. But if you look at the picture, it does make perfect sense. So in the picture, it's telling me at negative 0.3 seconds, the height is 0. And that's correct. If we went back in time and kept tracing it, we would be back in the water at negative 0.3 seconds. But that doesn't actually help us because our whole point of this problem is to figure out where they landed in the water after jumping. So this is going to tell us that it's at approximately 2.3 seconds. So therefore, the diver hits the water approximately just going to use short form there, approximately 2.3 seconds after jumping. Or I guess after diving. What's the term here? After diving? I don't know. I guess after jumping. Works just fine. Okay, so both of those problems that we just did were basically the exact same problem. We found the vertex form by using our completing the square. Once we did that, we had our maximum by determining our vertex. This also allowed us to figure out how long it took us to get to that maximum. And then then we had usually one other follow-up question. In this case, it was, well, how long did it take you to actually get back into the water? How long did it take you to get back to a height of 0? So every question has the exact same wrapper, if you think about it, when they are this type of problem, right? So if you remember, these are what we call formula problems. Now let's get into money problems or revenue problems. Now revenue basically boils down to how much money did you earn? That's what revenue is. Revenue is all about how much money did you make, all right? So money earned. And the way that we calculate money earned is always the exact same thing. It's always the price of whatever we're selling multiplied by the item that we're selling. For example, if you were selling shoes and you were selling shoes for $50 each and you sold 3 pairs of shoes, that'd be you had 3 items multiplied by 50. So that gives us $150. So items sold. Okay. I don't know if you know the symbol, but this is the symbol for number of items sold. Price times number of items sold. Sometimes we'll shorten this down and just to a simple formula. R is equal to P times I. Okay. So why do we want to know this stuff? Because this is going to allow people to understand how to properly charge you in order to make the most amount of money possible. Unfortunately, that's kind of how it works. So Mr. Wonka, very famous chocolatier, works at the Wonka Chocolate Factory, makes sense, where he charges $4 for a large bag of rainbow gumdrops and sells approximately 120 bags per week. Okay. He discovers that for every 50 cents decrease in price, he'll sell an additional 20 bags. Oh, that's good news. So what would be the maximum revenue that Mr. Wonka would make? Now, we weren't given an equation this time. What we have to do is we have to come up with our own. So we have to think about it. What are we trying to do? We're trying to talk about maximum revenue. So that means we're trying to find a calculation for revenue. Remember, revenue is equal to price times items. Price times items sold. So let's think about this. What does that mean in our context? So let's write this nice and full. Revenue is equal to price times items. Now let's think about this on the side. What is the price? Well, the price is $4, right? It starts out at $4. However, it decreases. So we're going to subtract. How much are we subtracting? We're subtracting 50 cents. Okay, so the price is $4 minus 50 cents. However, we do 50 cents many times. How many times? However many times we need. Oh, that's an unknown value. That's our first step, ladies and gentlemen. Our first step needs to be our let statement. So let's let X be the number of price reductions, of, let's say, 50 cent reductions. 50 cent decreases. So now when we look at this problem over here, this price is $4 minus X times the number of 50 cent decreases. So if there were 2, that'd be 2 times 50. So that'd be 4 minus $1, which would be $3. So that's where we get the price from. Okay. What about items? So right now we're looking at the price is 4 minus 0.50x. That's our price. But we need to multiply that by our number of items. Well, what about our items? Well, initially, our items sold was 120 per week. However, for each 50-cent decrease, we sold more bags. Oh, more. That means we're adding. How many more? 20. Multiplied by the number of decreases we have. Okay, so now we have our number of items, 120 plus 20x. So this is our revenue. I'm just going to put R here. Well, that's good news. However, this is not an equation we can work with. We can't put this into vertex form. I know some of you are looking at it and says, oh, that's factored form. Yes and no. That doesn't really help us to what we're trying to do here. So what we need to do is we need to expand. We're going to expand and simplify to put it into standard form. So that means you need to FOIL out the values. All right, so let's do that. 4 times 120, that's 480. 4 times 20x, that's going to give us plus 80x. 50 cents times 120, and it's negative 50. So negative 50 cents times 120 is going to be negative 60x. And a negative 50 cents, so negative 0.5, times 10x is going to give us negative 10x. Now we need to collect, 10x squared, I should say, 10x squared, because we have an x times an x. Now we need to collect all of our like terms and reorganize this thing. So we have negative 10x squared. We have 80x minus 60x, so that's plus 20x, and then plus 480. Now, we're gonna do the same process we've been doing now. We're at the point that we were in the previous questions from the earlier in the lesson. We're going to use our strategy to create our vertex form here. Okay, so we're going to complete the square. So first thing we need to do is factor out the entire a term. So that's the negative 10. Negative 10. And remember, we're factoring it out from just the first two terms here. So negative 10x squared just becomes x squared. 20 divided by negative 10 is negative 2x. And then we leave the 480 on the outside. Okay. Now we have our negative 10. We have our x squared minus 2x. And now we need to divide the second term by 2 and square it. So 2 divided by 2 is 1. Squared is 1. So we're going to plus 1 and we're going to minus 1. We still have our plus 480 on the outside. Okay. Now we got to bring this minus 1 to the outside, but we have to multiply it by a to do that. So negative 1 times negative 10 is just going to give us 10. So we have, we have negative 10 times x squared minus 2x plus 1. And on the outside, we have plus 480 plus 10. Now we're definitely not done yet, so we got to keep going. So now we're going to combine those two terms. That's going to be 490. But inside, we can see that we have a perfect square trinomial, like usual. That's the whole point of completing the square. So this is going to be equal to negative 10 times x minus 1 squared plus 490. Now, I know what some of you are thinking right now. We keep getting the same value for h, the same thing on the inside. That is absolutely just a coincidence, ladies and gentlemen. It's not always going to work out that way. So please don't make that assumption. All right, so we now have our entire quadratic relation. So now we can pull out our vertex. Our vertex is located at 1, 490. So what does that mean? That means that we have a max of 490. So therefore, what would the maximum revenue be? Therefore, the maximum revenue would be $490. Okay. What price will maximize Mr. Wonka's revenue? Well, what do we actually know here? Well, we know how many decreases do we have? We have one decrease. Decreases. Oh my goodness. Can't spell, and it's lagging on me right now again. Let's try this again. So that represents the decreases. Okay? So that means we had one decrease. So what are we trying to calculate? We're trying to calculate price. So let's substitute that decrease into our price formula right here. So since there is one decrease to maximize revenue, therefore, all right, not therefore yet. Now what we're going to do is we're going to say price is equal to 4 minus 0.50 multiplied by 1. So that's going to be equal to $3.50. There's your answer. So therefore, the price would be $3.50. Okay, so our revenue problems are all going to be pretty similar to this. We have to create an equation. We're usually going to have to multiply it out and expand, and then we're going to use completing the square to put it in a vertex form, and then we're going to find the max or minimum based on that. So let's go down. Let's go down to example number 4. I think this is the last example of the day. Yeah, so this is the last one. This one's a bit longer, but it's still the same question. Alrighty. So a movie theater sells 3,000 tickets a day at a price of $6 per ticket. Okay. It has been determined that for every 30-cent increase in price of the ticket, the theater would get 100 fewer customers. So first of all, we have to understand what is going to be our let statement again. We need to represent our unknown value. So in this case, our let statement is going to be that unknown again, which is the number of 30-cent increases. So let's say let X be the number of 30-cent increases. All right, now let's go to the question. What would be the current revenue, what would the current revenue be with no price changes? Well, that's easy. The current revenue with no price changes is just R is equal to P times I. Well, what is the current price? The current price is $6. And the current number of items is 3,000 tickets. So we have 3,000. So that means the current revenue is $18,000. Therefore, the current revenue is $18,000. That's not bad. Okay. So what would be the maximum revenue? All right, now we have to get to work. So let's think about what our price value is. Remember, R is equal to P times I. R is equal to P times I. Okay. So what is going to be our price? So our price calculation is always going to be our starting price, which is $6. And now we're increasing, where these are price increases, right? So we're adding. How much are we adding? We're adding 30 cents. How many times are we adding them? X times. We don't know how many times, X times. Similarly speaking, for our items, it's going to be the same idea. What price, or what is our starting value? Our initial number of items. That's 3,000. Okay? And how many are they changing by? Well, we're getting 100 fewer this time. So we're getting 100 fewer customers. That means we're subtracting 100 for every price increase. Okay, so we have our items and we have our price. So let's put this all together. So we have 6 plus 0.30. We can just use 0.3 x, and then multiply by 3,000 minus 100 x. Okay, we got to expand. We got to use FOIL. 6 times 3,000, that's 18,000. 6 times negative 100x is negative 600x. Okay. 0.3 times 3,000 is 900x. Those are all positives. And then finally, 0.3 times negative 100 is going to give us negative 30x squared, x times x. Now we're going to rearrange. So we have negative 30x squared. And now we're going to combine our x's. So we have negative 600x plus 900x. That gives us plus 300x plus 18,000. Okay, we finally have a starting relation. But now what we're going to do is we're going to use our completing the square to actually put it into vertex form so we can use it for this question. So we have to factor out the entire a term. So, well, that was... I don't think undo likes my stuff here. Okay. So we're going to factor out the entire a term, which is negative 30. So this first term becomes just x squared. And then 300 divided by negative 30 is negative 10x. And then we're going to leave our 18,000 all alone on the outside. Numbers are quite a bit bigger this time. Okay, so we're going to leave this stuff alone. Negative 30 times x squared minus 10x. And now we have to, there we go. Half the second term, so 10 divided by 2 is 5. And now we're going to square that, so that's 25. So we're going to add 25, and we're going to subtract 25. And then on the outside, we still have our plus 18,000. So now we have negative 30, and that is going to be times x squared minus 10x plus 25. Now we're going to bring the negative 25 to the outside, but to do that, we're going to have to multiply it by negative 30. So that should be 750. Yes. So it's going to be, because negatives and negatives. So we have plus 18,000 plus 750. So finally, we're going to end up with negative 30 times, we got our perfect square trinomial, x minus 5 squared. And now on the outside, we have plus 18,750. So what does this tell us? It tells us our vertex. Our vertex is located at 5, 18,750. Now, in questions like this tells us our max or min, depending on the problem. This is our max. And this tells us our x, which is our number of increases. Okay, so what would be the maximum revenue? Therefore, the maximum revenue is $18,750. Okay, $18,750. Easy enough. So, what is the optimal selling price? Optimal means best. Optimal means best. So in our situation, it means whatever gives us the maximum amount of revenue. So it's asking us for the optimal price. So again, we're calculating our price. Well, we know our price is equal to 6 plus 0.3x. Well, we also know that x is from our vertex. Okay? So in this case, x is equal to 5. So we're going to substitute. 6 plus 0.3 times 5. Well, 5 times 0.3 is 1.5. So that means that we end up with price is equal to $7.50. Therefore, the optimal price is $7.50. $7.50. Okay, how many tickets are sold at this price? So this is the exact same question as the previous one. In this case, we're trying to calculate items. Well, what is our formula for items? Our items is equal to 3,000 minus 100x. What is x? X is equal to 5 because it's at this price. So we substitute. So we have 3,000 minus 100 times 5. So that's 3,000 minus 500. That means our number of items is equal to 2,500. Therefore, 2,500 tickets are sold at this price. All right. So those are the two types of problems we're going to see. We're going to see formula problems, or we're going to see revenue problems. In the next lesson, we're going to learn two more types of problems, and that will basically close up all we need to know for the first part of Unit 6. And that'll cover your first test up to that point. If you have any questions, make sure you go see your teacher, do all your practice work, and any extra work that your teacher affords for you. All right? Good luck.